Yeah, so thanks again for the introduction. I'm really happy to share some of the stuff that we've been working on. I've been thinking about Varves for a long time and worked on different Varve records in different capacities. And more recently have been working on some of these tools, which are well, some of them are specific to Varve records, some of them are more broad. So was really happy to get the invitation to come and share what we're working on. And there's sort of two main things I want to talk about today. So the first is this broader set, these tools for what we call age uncertain data analysis, and this is really about this new R package called geoChronR that's useful for any sort of age uncertain data. So this would include Varve records, but is much broader than that, and works effectively the same way across all of those. And then in some ways, this is sort of, moving backwards, because this is going to focus on how to, analyze the data after you've quantified the age uncertainties. But then at the end, I want to spend a few minutes also talking about how to quantify those age uncertainties specifically for Varve records. And this is some of the work that I've been doing along with my some colleagues and some students over the past several years. That's coming along, and wanted excited to have the chance to talk to you all about that too. Okay, so no further ado. So I want to start by talking about geoChronR. geoChronR is an R package. It is currently in press at geoChronology. You can go and read the discussion version. The final version should be here. Should be published, I think, within the next few weeks, which we're really excited about. This has been a long effort, something we've been working on a long time. The software, the R package itself, is also available. It's currently on GitHub, where we will be, once the paper is out, the sort of next major step for us is moving that to be on CRAN, to be a sort of an official, if you're used to working with R packages, R package, and so look for that in the coming months as we finalize that. I've been working on this project with Julien Emilge and Deborah Kiter as my two main co-conspirators, but we've had a lot of contributions from other people as well. So the big idea between geoChronR is to leverage the power of ensembles. Dealing with age uncertainties on the time axis, as I think all of you know, is something that's really hard for traditional statistics, and that typically the assumption is that you know the time and you're dealing with uncertainties in the Y variable. That's just not true with most paleogeoscientific data. And so to get around that, what we do is we take advantage of different statistical methods which generate a large ensemble, a large collection of similarly plausible chronologies, and then and essentially repeat the analyses across those. And so this can look different for different kinds of records. Largely, a lot of the work on this area has been done on tie point chronologies, largely radiocarbon chronologies, like you have here over on the left. Where you'd have, say, a handful of radiocarbon dates, and then each of these sort of faint red lines would represent a different ensemble, ensemble member, a plausible age depth history for this lake, and then so altogether it represents a broad set of uncertainty. But by simply repeating the analyses across each of the different alternative histories here, or a large subset of them, you can get a sense or start to quantify the age uncertainties. There are also, you can also create ensembles for layer counted chronologies as well. Like I said, less work has been on this, but once the ensemble exists, then geoChronR happily uses either of these. Okay. Thanks. You also mentioned this in the introduction. A lot of the same folks that have been working on geoChronR were instrumental in developing this linked paleo data, or lipid data format, which was largely developed because of the needs of geoChronR. We needed some sort of way of inputting and handling these ensemble data in a way that tracked metadata and then would plug into these tools, and along with other needs, developed this idea of lipid, which is now, happy to say, being used really broadly in a lot of synthesis efforts, and there's thousands of data sets that are formatted this way. I'm not going to go into it in too much depth, but the idea with lipid is that you can encode and structure a whole bunch of metadata about paleogeoscientific data set, including its metadata about where it is in space and the publications and the funding, and then critically all the data and metadata about the chronology and then about the environmental phenomena of interest that you're measuring. Here in this chart on the right at the bottom, you see this whole section called chron data, which is short for chronological data. In which case you would have the measurement data. So this could be the radiocarbon dates that you measured, and then models that describe those, which would include those ensembles as well as the distributions and information on the methods. And this is all stored inside the file. And this is what this is sort of the native language for geoChronR to work with. This can be complicated, but there are a couple ways of getting data here. So we have this website that's called the lipid.net playground, which is by far the easiest way to create a lipid file. It will sort of walk you through how to upload and enter your data and structure this in a way that you can have a data set that you can start working with in geoChronR. As I also mentioned, there's now thousands of data sets that are in lipid, many of which include ensembles, and many of them are on this website called lipidverse.org, including lots of the big synthesis projects that I've been involved with. It's easy to access and download a bunch of lipid files there, which would then be ready to use in geoChronR. Okay. So there are four major classes of analyses that are set up presently in geoChronR that work, and these are a pretty good survey of some of the really common techniques applied in the paleoclimate sciences: correlation, regression, principal component analysis, and then spectral analysis. And again, the idea on all of these is that we're going to take advantage of the ensembles and then repeat the analyses across a large subset of those ensembles, and then try to visualize those results in a way that help us assess the impact of age uncertainty. So I'm just going to run through each of these examples. This is also each of these examples, and the examples I'm going to go through are in the manuscript that's in geochronology, and they're also available as tutorials on the reference website for geoChronR. And so here's the URL, and I'm happy to post this link again later. This has all the sort of help documentation. That reference tab up top describes every function in the package and what it does. But the tutorials button is especially relevant. Oh, sorry about that. Okay. For this, and so you'll see if you click on tutorials right now, there's 9 of these, and those top 5 include essentially everything that I'm working through. I'm going to be talking through today. You can see that again there, and also the code and all the specific steps that were used to create each of these graphs is all there. And so this is a really good way to get started with it, is to try to just reproduce the examples that are listed here. So when you click on one of those, this is an example from the PCA. I'll show you this figure later as we're talking about PCA, but you also see that there's some text that describes it, and then the code that was used to produce to create each step in the analysis is all listed here in the tutorial. So this is a good way to get your head around how to use this package. Okay. But now for a bit more of an overview as we go through these things. So I'm going to start with correlation. This is maybe the single most common thing that many of us are doing with paleoclimate data, and that age uncertainty absolutely impacts quite a bit. So as a classic example, we took these 2 long data sets. This is just one stalagmite, one speleothem from the Hulu cave record, which spans this interval from about 50,000 to about 35,000 years ago, and then a subset of the GIST2 temperature record, which are described as they're broadly related, and there's a whole bunch of research going into that, and sort of whether or not these things are correlated or related is way beyond the scope of this talk. But as a sort of simple example of how age uncertainties impact correlation, this works well for us. This plot is produced by geoChronR, and it's kind of one of the ways we like to visualize the data. There's 2 things here. You see the black line and the gray shading shows the distribution of how age uncertainty impacts the distribution of the values across the full ensemble. but it often tends to smear out a lot of the local variability. So sometimes we'll also put these sort of a handful of these red lines or these traces on top of it to show what individual age ensemble members look like. And what we're going to do is we're going to take each of those individual age ensemble members, randomly select them between the two data sets, correlate them, store those results, and then repeat that, and then try to summarize the results at the end once we have a large subset of that. So this is the result. So if you take 1,000 of those different ensemble members, correlate them, and then present those correlation values in a histogram, this is what you get. So the x-axis here are the R values, and then the y is just a histogram, so it's showing the frequency of that. The red lines, vertical lines, show you the quantiles of that distribution. And then the colors on the bars tell you whether or not that passed a significance test. In this case, this is a Pearson correlation coefficients or standard student t-test. And you see that 13% of the ensemble members are significantly correlated. Most of those have a negative correlation. You see that most of the significant ones have a negative correlation that's less than negative 0.25, but there actually are a handful that were high, have positive correlations that also passed. So here we clearly see there's a pretty big impact on age uncertainty on this specific correlation, and it definitely affects whether or not it's significant. Most of the correlations aren't significant. Now, of course, this is the simplest approach, and it's ignoring some of the things that we know mess with significance between correlating to paleoclimate data sets. And the big culprit here is autocorrelation, the fact that there's memory in both of these records, which would likely artificially inflate correlations or the significance of correlations. So geoChronR has a handful of different ways, of more sophisticated ways of assessing significance between correlated data sets. And I'm just going to run through those real quick, and we'll see their impact. So these would essentially be options that you could choose when you're doing the analysis. The simplest one is called the effective N adjustment. It estimates the impact of autocorrelation on the degrees of freedom, and then reduces that. It's the simplest approach, and it's often overly conservative, especially for data sets that are quite autocorrelated. So if they have, if they're pretty highly autocorrelated, you tend to get results like this, even when there are potentially real correlations. The correlation values go really, really low. So in this case, there's none. We don't see any that pass the test. But this is typically not the best one to use. So there's two other methods which are Monte Carlo based that are going to take the input data and then try to simulate a bunch of random data that observe similar characteristics. So this one's called iso-persistent, in that it preserves the persistence of the data that we're correlating. So it's going to have the same autocorrelation structure. It's going to generate a whole bunch of random data that look like the data in that they have the same autocorrelation structure, but then otherwise are random, and use that as a null hypothesis. So doing this, you actually get a similar result, and you actually see there's not, with this approach, you still get about 12% that are significant. And there's one other method which I'm going to tell you about in a minute, but there's one other correlation phenomenon that we want to be aware of, especially when we're calculating thousands of correlations, and that's called the false discovery rate. And this is the idea is that if you are calculating hundreds or thousands of correlations, you're going to start to expect some of those correlations to be significant just by random chance. And so, this is called the false discovery rate, or the look elsewhere effect, is that if you eventually just keep correlating things, you will eventually find something that's significant, and you can't just focus on the significant ones. This is I would say, a fuzzy area for ensemble correlation still, about whether or not this is you want to consider this. It's generally a good idea to consider it. And so it's, we turn it on by default, and then this shows up here as these, once you've adjusted for the false discovery rate, you see this lowers the significance. I'm going to show you one more combination here. And again, I know this is a lot, and the idea is that if you want to follow up again and really dig into the results, going through the manuscript or the tutorials will probably be more instructive. Okay, so the last one is called the isospectral method. So instead of trying to preserve the persistence, it tries to preserve the spectral characteristics, which often will include the persistence as well. What it does is it has the same spectral characteristics, but it randomizes the phase. And include it using this approach, the isospectral approach, and the false discovery rate are the standard, the default options in geoChronR, and they're often the best. They're sort of the most rigorous, and they're well respected in terms of their statistical rigor, but may not make sense for every circumstance. So I want to take a step back. And then, so we have this result. We see somewhere between 0 and 13% of these ensemble members are showing a significant correlation, depending on how you approach this. And so then we often have this question. It's like, okay, well, in this case, it says, so are they correlated or are they not correlated? In this case, yeah, it seems pretty clear. For the most part, it looks like most of these data sets aren't. You don't see a significant correlation. And there's lots of reasons why that may be. Correlations are relatively, it can be a relatively brute tool. And there's lots of good reasons to think that these two data sets are, actually connected for climatological reasons. And we're not, the point of this is not to disprove that or anything. This is just an illustrative example. But this often doesn't come down to sort of, so what if you get 50% of them are significant and is that now a correlated data set with age uncertainty or not? And so there's no silver bullet for that in terms of saying, yes, this is correlated or no, it's not. And so it's good to think of this as sort of a guide of a sense of assessing the impact of age uncertainty on the correlation. Just that sort of instructively here. So if we take this as if we look at a best case scenario and just take the Hulu record and correlate it with itself with age uncertainty, so as if it was essentially the exact same data set, but we're going to treat the ages as independent, and then do the same analysis, you find that you don't get correlation values of 1. This isn't surprising. Age uncertainty is even in the best case scenario is going to destroy a lot of the correlations between them. So you do see that in this case, doing this, you have values that are well below 1, but also that are consistently significant. So again, the lesson here is that this is it's good to think of this as a map and as a tool that's relatively easy to sort of explore whether or not age uncertainty is going to destroy your correlations, but is not going to necessarily give you a definitive answer that yes, this is correlated or no, it's not. Okay. I move on. So the rest of these, I'm going to spend a little bit less time sort of delving into the detail of the stats, just because, again, I want to have time for other things, and I know that can be a lot in this kind of format. Okay, so going into regression, in this example, what we did is we recreated this paper that that I was involved with from a few years ago, where there was this spectral reflectance record, which had an interesting correlation with instrumental data. This is from northern Alaska, and the goal was to use that relationship, the observed relationship between temperature and reflectance, this reflectance index RABD, to create a calibration in time and then estimate temperature back in time. And so the question, one of the questions we explored in the manuscript, and one of the things that you can now do in geoChronR and that we reproduce here, is how does age uncertainty not only impact the reconstruction, but how does it impact that calibration? Just because, as you can see with the sort of fuzzy red lines, as you shuffle the data around in the 20th century, that's going to change the correlation and regression structure that you would use to make to develop that. So if you're doing this, and this is sort of the focus, so regression is built in, and you could use it for other types of regression, but this example focuses on a calibration approach. So here's the same figure we've been looking at with these correlation distributions, and this is what you get when you correlate those instrumental data with the RABD data over the 20th century. Again, this is a good example of it not necessarily being a cut and dry answer. In this case, you see generally high distributions, but with this tail that shifts down, so shifts to the left, where they become certainly insignificant. So in this case, it's 72, about 73% of the correlations are significant. It's a good chance this is a real relationship, but it's also it's within, and so it's good enough that it was worth moving on and considering the regression. and then this is the sort of dashboard that comes out of the regression analysis. So there's a lot here, so I'm going to spend a few minutes going through this. At the top left, you have the predictor and the predicand. In this case, the observed temperatures and then the age uncertain data that we're going to use to try to predict the temperatures. We have a scatter plot here in the middle, top middle, that's showing this relationship. And transparency here is highlighting the where you have a higher density of data and where you don't. It's pretty messy, but also the transparency on the regression line as well. And so you do see this big cluster of sort of a steeper slope, which is representing most of those correlations, but then a significant sort of fanning towards lower slopes where, because due to age uncertainty, this relationship is much weaker. That would then be captured here as well. So now what we're going to do is we're going to take all of these different regression slopes, which are summarized in the top right. You see the distribution of the slopes and intercepts, and again, mostly higher slopes, but a real chance of lower slopes there represented in that left tail, and then correspondingly, the intercept which is going to have the opposite impact. And so now, instead of using a single calibration model, we now have 1,000 calibration models which account for age uncertainty. And so when creating the reconstruction at the bottom, which goes back for the past 6,000 years and translates RABD into temperature, we're thinking about the age uncertainty in the timing of those RABD values, but also the impact of how that introduces uncertainty into the calibration model. So that ends up spreading out some of the uncertainties in the calibration more and better capturing the uncertainty in that instrumental relationship. Okay. So next, I want to talk about principal components analysis. This is the first and the only of these four methods where we're going to be considering more than just a couple records, where you might be looking at a large network across space. This is this idea of doing age uncertain PCA or EOF has been around for a decade now. Kevin Antikaitis and Jess Tierney published a paper on this back in, I don't know, 10 years ago, 2012. And this is largely using the same approach, but hopefully is much easier to implement in geoChronR than trying to cook it up yourself. As a test case here, I'm going to use a network of layer counted, almost exclusively layer counted records, very high resolution records from the European, sort of the Atlantic Arctic, that Daryl and I published on a few years ago, where we created a bunch of ensembles that are available for in this database that we can use now in geoChronR to do a PCA across this region. So it's a mix of ice core records and lake records, mostly Varve records. One nice things that you can do in geoChronR is just plot all the data here without age uncertainty. And so all the blue records are delta Dano records from ice cores. The yellow and green records are Varve thickness or mass accumulation records, or this other the radiographic darkness records. So it's a bunch of Varve. It's 1, 2, 3, 4, 5, 6 Varve records, and then the rest are ice core records. With different spatial coverage and all with their own sorts of bits of age uncertainty related to layer counting. So again, the same idea is we're going to do this the same way we did in correlation and regression. We're going to randomly sample a ensemble member from each of these age ensembles, do the PCA, store the results, repeat that 1,000 times, and then summarize the results across that. So here we have the scree plot. This is a typical diagnostic plot for a principal component analysis, where you look at the amount of variance explained in each component number as they go down from 1 over here, in this case, to 8 on the right, and compare that to a null model, typically sort of a red noise model, to see, are we explaining more variance than we expect to based on that model. And then typically when the data cross over the null line, you stop. You only consider components which have more variance explained than null. So as typical, age uncertainty complicates this, and so now instead of having a single estimate of variance, we now have an ensemble of estimate of variance that changes across the ensemble. So the first two components are clearly, well, the first one is very clearly well above what you'd expect. The second one you see does start to overlap the uncertainty. So certainly the black line, which shows the median, the gray line, the darker gray, which would show the 50% highest density interval, and then the light gray would be the 95%. So the light gray overlaps, and so there is within age uncertainties a chance that only the first two would be significant. But given that it looks like for the most part the first two would rise above, and then by the time you get to the third one, it's pretty much 50-50 whether or not you're above the line or not. It makes sense to consider the first two and maybe look at the third one. Again, there's no specific rule here. It's sort of a judgment. It's a judgment call. So in this case, we're going to look at the first two principal components, and now we get to think about the impact of age uncertainty in both space and values and time. So we added another dimension, which means we have to be creative with how we're going to visualize this. So the loadings that come out of the principal components have uncertainties now associated with age uncertainty, and then also the principal component time series. So we're used to looking at the time series now with their uncertainties. We see this. So if you look at the top, at the right panels, you see the first two principal components in time and their variance explained, which vary by about 1% across the age uncertainty. PC1 seems pretty robust to age uncertainty, with certainly some things as you go further back, but a similar pattern. As you get to PC2, it gets a bit more variable, but still there does seem to be a sort of coherent century scale pattern in which stands out above the uncertainty. For the spatial loadings, there's a few things happening. So what's plotted here is the median of the loadings is the color, and so. And the top one, you see they're pretty much all positively loaded, but some of these sites are going to be more vulnerable, more sensitive to age uncertainty than others. And the way we visualize that in geoChronR by default is by the size of the dot. And so the more uncertainty, the smaller we make the dot, so that we draw your eye to the sites which are most robust. So the uncertainty on the loading ranges from 0.3 to 0.7 across the 95% confidence interval, and again, the bigger the dot, the lower the uncertainty. So again, not going to have time to go into the science here. There's some interesting patterns that emerge. It's more about the method and how we're going to try to visualize some of the uncertainties here. Okay, and then finally, I want to touch on spectral analysis. There's a lot that goes into spectral analysis, and there's a lot of choices to be made. I'm not going to go through all of these. Just as a quick example, and as the example that's included in the tutorial, I'm going to show this. We're going to zoom out in timescales and now look at a very long record, which is showing temperature over the past 5 million years, where somewhere we expect spectral analysis to work really well. So here again, we see the steady cooling, and actually the way this ends up getting visualized here is a little hard to make out, but there are strong glacial interglacial cycles present here in this data set. Something I also want to show with this example is you'll notice that the sort of aesthetics of the plot look pretty different. So far I've been showing everything with the default geoChronR style, which in all the visualizations, or pretty much all the visualizations in geoChronR, use the ggplot2 package, which most I think our users will be pretty familiar with, and exports them as sort of standard ggplot objects, which makes them really easy to customize. So in this example, my colleague Julian sort of highlighted how if you wanted to customize the look and feel of the output, it's pretty straightforward to do that. So you can see that in the tutorial. Okay, so again, same idea. We're gonna do a spectral analysis across a bunch of ensemble members and summarize the results and think about what that means. So there's 4 spectral techniques that are presently available in geoChronR. Because typically paleoclimate data aren't evenly spaced, we can't use MTM, which is the standard, without doing some sort of pretreatment. So there is an interpolated MTM. That's what's shown here. We also have Redfit and Lomscargel, which are two variants on techniques which are designed to work with unevenly spaced data, which is great for paleoclimate data, but has other issues. And then there's new spectral, which is a sort of a more I don't know. I'm not sure how to describe it. A sort of less commonly used method, but also also same idea. It doesn't require evenly spaced data, has some advantages, but in the R implementation is really, really slow. And so it does not work well for ensemble method unless you have a lot of time. Okay. So here we see, again, so what you'd expect. So, irregardless of age uncertainty, we see these, the key periodicities that you'd expect to see popping up above the confidence level. Which is great, and then compare the same result to what you get if you use RedFit, where it's actually a little bit fuzzier, and you see in general a flatter spectral slope. So this is not uncommon with RedFit. So one of the compromises with being able to handle unevenly spaced data is it tends to flatten out and smooth out the spectra a bit. So so if your data are nearly regularly spaced, you can often get better results with MTM, but if they're really irregularly spaced, MTM can be really biased. So again, not going to go into too much depth here, but there's a lot of depth on the website if you go walk through the tutorial if you're interested in the spectral methods and these choices. Okay, so yeah, I think in the next 10 to 15 minutes or so, I want to so move away. So that was a really quick survey of the things that are available, the sort of standard data analysis that are currently available in geoChronR. It also has a lot of sort of the foundational tools that you would need if you wanted to develop some sort of custom analysis, which is often important depending on scientific questions. These tools are really great for sort of out of the box for some preliminary analysis, but if you get down to it and try to really understand if a marginally significant correlation, for example, is worth pursuing, you might have to develop something a bit more customized, which there's a lot of tools in geoChronR that can help with that. And now I want to sort of think about the other side. The first side of this is that, so if you have a Varve record or a bunch of Varve records and you'd like to address these questions and they don't already have age ensembles, what tools are available to do that? geoChronR includes tools for creating age ensembles. 4 of them. So again, and most of them are focused on type point chronologies, but it also does include a method called BAM. So this is called Banded Age Model. This is published, I guess, in 2014 by Maud and Julian. And the idea here is that essentially it's simulating overcounting and undercounting. And I came up with some visualizations that hopefully help explain what's going on here in some of these different approaches. So hopefully you can see this animation shuffling around and this sort of simple visualization of some different varves and different realizations of those varve thicknesses showing up. Okay. So what's great about there's a few things that are really great about BAM. So first, it's in geoChronR. It's really easy to use. It's essentially if you have a varve sequence, all you would really need is an estimate of the probability of overcounting or undercounting. So how likely is it that any given varve is overcounted or undercounted? So in this example, I'm using a 5% chance of overcounting or undercounting. And then it uses a couple different, there's some options for the statistical model, but like a Poisson or Bernoulli distribution to effectively simulate whether or not a varve is overcounted or undercounted, and then handle the fallout for that and builds up a whole ensemble for you. It's really easy to use, and all you need is the years and then this estimate of overcounting and undercounting. And this is what it would do. It will sort of it'll shuffle varves around, combine them sometimes or not combine them, the counts of them to give you this ensemble, which will then you can use. So it's really useful, especially for sort of first analysis and easy to do. So I would encourage you to try that if you're interested. There's some downsides to this though. So there's several shortcomings for varves, which have led us to want to do some other things. So as you may have or not have noticed in that animation, the total thickness of that my 10-year varve sequence there was changing as it change the counting. So it doesn't. BAM is not aware that this is there. It wasn't designed with varve thickness records in mind. And so it will essentially average. It's a reasonable approach, but if you're trying to think, okay, I know that there's a meter of sediment here, there's no uncertainty there. It's just the number of varves that's uncertain. It doesn't recognize that. So when it if it says, okay, this was undercounted, there should be 2 records. It's not going to split that and keep the thickness the same, and vice versa. It also, you can only apply a single overcounting. Well, they can be different. The overcounting, undercounting can be different, but they can't change down core. And that's something that when we were doing varve counting, we really wanted to improve on, because there's sections in the cores that we work on, I think, in every varve sequence where the varves are really well delineated, and we have a lot of confidence that we can count them with pretty low overcounting, undercounting rates. And there's other sections which we do not have that confidence for, and it'd be really nice to model that, incorporate that in our uncertainty quantification. And then the third piece that we wanted to improve on is that it doesn't know anything about this idea of marker layers, that there are, as you go through the core, sections that have uncertain counts, but then these identifiable bands that we know occur at the same time. We just don't know when that time was typically. And then, or with some level of confidence also. So we want to be able to say, okay, we're 90% sure that this is a marker layer that occurs at the same time, and that the amount of time between these 2 marker layers should be the same. So we've been working on ways to improve this. I guess this is a couple years ago. We first published results from a Klutna Lake, this Varve record. That includes this Varve modeling. Essentially, it's very comparable. It's conceptually very similar to BAM, but it incorporates some of these concepts. So now what we're going to do is we're going to have marker layers with some level of confidence, and then we're going to know that the depth between those marker layers is stable, and so that as we simulate the changes in the counting, from overcounting, undercounting, the total thickness is going to stay the same, and it's going to intelligently combine or split varves based on the metadata that we assigned to those varves when we were counting them. So this also means that every varve can have its own undercounting or overcounting probability. We typically don't do it that granularity. We typically will assign 3 or 4 sort of confidence levels, or sort of quality codes is typically, and so these are and then each of those quality codes then get paired with overcounting, undercounting rates that change down core. So then in this example, there was 5 cores, and so we take this, and so here's this is a typical type diagram you may see. This was from the paper. There's a whole bunch of these marker layers that go between these 5 cores, and so this animation here is showing that so imagine we're between 2 of these marker layers here. Each of them have slightly different thicknesses. You can see that the thickness from each core here is somewhat different, but between the 2 marker layers, we're really confident that it's the same amount of time, or however confident we are, whatever the certainty is on those marker layers, that we don't know how many years it is between each marker layer, but we know that it should be the same. And so what we do is we simulate the overcounting, undercounting probabilities for every core until they all give the same answer. So in this case, there was 10 in my fake example. It simulates. In this case, it found that there was 10. It might not always find that there was 10. Sometimes it'll find that there was 9, and sometimes it'll find that there was 11. And this animation is only going to find 10 because that's all. I stopped it there, and then it repeats. And so we we simulate the number of counts between each marker layer, go down through all the marker layers, store all of those thicknesses for each core, and then that becomes one ensemble, and then we repeat this and do this again until we have hundreds or thousands of these ensemble members, each of which has its sort of alternate plausible varve counting histories that also incorporate things about changes in varve quality. It knows about marker layers. It knows that the thickness needs to be constant as we go through the course. So doing this, we did this with Lake Klutna, and we came up with these now varve counted chronologies that have uncertainty and uncertainty structure across them. Here's this example. In this case, you can see there's a comparison to radiocarbon data, but the radiocarbon data don't inform the counts at all. and it lets you it let us. Oh, I didn't include that, but there's a bunch of tephra in this core, and so now we have age distributions that take the counting uncertainty into account, and we can look at now the age distributions of the tephra in the core. So so that was a couple of years ago, and then more recently, Stephanie Arcusa, who just finished her PhD at Northern Arizona University, has been working on improving this and innovating on this, and so taking this idea and then adding in radiometric dating. So in this case, we're looking on this intermittently varved core. It's where the quality really changes, and so there's some sections that are really hard to count and some sections that are great. And then incorporating, so using this Varve modeling approach, but then using Bayesian learning to update the undercounting and overcounting probabilities for different Varve codes based on the radiometric dates. So here what we're trying to do is optimally combine that Varve model with, in this case, radiocarbon and lead-210 and cesium dating. And so essentially answering the question, what if we trust our Varve model in our counting and we trust the radiocarbon dates, what does that imply about the overcounting and undercounting probabilities to maximize the agreement between the Varve counts and the radiocarbon data? And so this is a manuscript that is just about to be submitted here in the next probably a month or so to geoChronology. So that should there should be a discussion version of that available soon. So let me just show the idea here. Is that here's the sort of original counts there in the different from different cores and different observers in the gray, orange, and blue bands. And then the idea is to integrate all the counts and all the observers also with the radiocarbon dates and come up with a chronology. And so in this case, the radiocarbon dates would imply, or to get agreement, it would imply some pretty significant undercounting of sections of the core. So in this case, it simulates that undercounting primarily in the poorly counted, or sorry, the harder to count intervals, and then gives us this new chronology here in green, which doesn't follow just the Bacon chronology. It has a different structure and knows about the Varve thicknesses and how they vary down core, but it also knows about the radiocarbon dates. So it's sort of an optimal agreement there that's trying to incorporate all the different sources of information. So really excited about this. The code for this is on my GitHub. It's largely stuff that Steph has worked on, and then some of the varveR code from the Klutna paper. It's definitely it's not as easy to use as geoChronR. So we're hoping to, after this paper gets out, to spend some time making this an easier approach and maybe ultimately incorporating it into geoChronR. But because it involves a lot more than BAM, because you have to have the Varve codes and all the marker layers have to be defined, and quite a bit goes into this. So I'm really interested in having people check it out and feedback on it and contribute to that. We love other people that want to code with us. Be great, but just as a warning, if you play with geoChronR and enjoy working with that, this will be a little bit tougher to work with. And last, I wanted to I think Steph is on the call, and so if you have questions about this, I may very well direct you to her because she'll know more of the answers about this than I do. Okay, I think that's that was the last thing I wanted to talk about. So I'm happy to answer any questions about any of this, or either now, or you can get a hold of me later with my email or on Twitter. You can also find me there or on GitHub.